and today I'll be covering the available options and recommended procedures for using Python on Summit and our other IBM Power Systems. Python's supposed to be easy, but it's often the case that Python environments on a shared resource, especially when parts of your workflow or research have different requirements in terms of Python major version, extensions, or external dependencies. They can wind up looking like this. This is a disturbingly convoluted yet common and often broken example of what can happen to a Python environment. So our main goal in what we provide in terms of Python interpreters and extensions is to minimize our influence in turning your Python environments into something that looks like this. And so to begin, I'll cover what we're providing on Summit and Ascent and Peak. We are trying to move away from providing all sorts of Python extensions as separate environment modules. And the easiest way to do that is to give users a all-inclusive Python environment. We are doing that through the Continuum Anaconda distributions for PowerPC 64LE. The Anaconda distribution will give you most of the common extensions that people like to use out of the box, so you don't have to load any additional modules. It's all there. There's some downsides to using Anaconda. We'll kind of cover all of that as we go through these slides. But if what comes in the Anaconda distribution is not what you need out of the box, they can be easily extended using Conda environments. The other way that we provide Python is through environment modules that offer a native Python interpreter. We also do provide some Python extensions through additional environment modules, but I recommend that you don't actually use those if you don't have to. It's not really feasible for us to maintain the outrageous combinatorics of Python packages, external dependencies, Python versions, different versions of external dependencies for Python bindings for things like HDF5 or whatever, and then things like MPI for Pi for every new release of Spectrum MPI that we get. What looks like a simple upgrade, as far as what we present in terms of modules, is actually often like thousands of builds on our end. And if you guys have used Titan, you might have some experience that that's not really practical, and it leads to the environment modules not always working the way that one would expect them to. So rather than do that, I would recommend that people, if they're going to use a native Python interpreter from an environment module, use it to create a virtual env and put the extensions that you need in that virtual env. And that way you can put exactly what you want in there. It's isolated from the rest of the Python interpreters in the environment. And as you change which packages you're using, you can upgrade individual packages in your Python environments without having us break them for you. And then lastly, if you don't want to use either Anaconda or Python from an environment module, DIY is always an option. And it seems to be a popular option. We have a lot of people who will install Miniconda in their own areas and just use that. As far as I know, most people who deploy their own Python use only Miniconda. I'm not exactly sure anybody's ever used a full Anaconda or installed their own bare Python interpreters, but those are also options. And the benefit of that, of course, is then everything is under your control. It's absolutely stable for the lifetime of your project. Okay, so to run through how to use the Anaconda that we provide, it is made available via environment modules. Because Anaconda being in your environment will conflict with other Python interpreters being in your environment, the module for it is actually called Python. And that's done to prevent you from loading 2 or 3 different Python interpreters at the same time and having them all step on each other. The version number for the Anaconda modules will be the Python major minor micro version dash Anaconda Python major version 2 or 3, and then the Anaconda release version. And so right now, that's only Python 3.7.0 for Anaconda 3.5.3.0 and Python 2.7.15 for Anaconda 2.5.3.0. When you load that environment module, it will change the Python user base. It does that automatically. It sets the environment variable to set your Python user base to a unique location for that machine and that interpreter, that Conda environment. So you can safely use pip install -- user when using the Anaconda modules. It will put those the packages that you install in a place that won't be used if you move to another machine or another Python interpreter. It's not necessarily true for the other Python, the native Python interpreter modules. And if you want to use a unique Python base for those modules, you have to set it explicitly yourself. One of the pros and cons to Anaconda is it heavily relies on precompiled binaries. Everything you install on using Conda, which is Anaconda's both package manager like pip and virtual environment manager like virtualenv. So Conda actually behaves similar to pipenv, if anyone here has used that tool, which we don't provide on our machines just because of the way it works, putting everything in your home directory. It makes it easy to install packages because all it's doing is pulling down precompiled wheels or something similar to a wheel. But the downside to that is what was used to build that precompiled binary might not be actually usable on an HPC resource. Usually whoever builds these packages makes assumptions about the glibc version available on the machine, that if that is a problem that afflicts Titan, but also things like CUDA version or MPI. Most of them are built against specific versions of OpenMPI. If a package that Conda can install for you is built against or requires MPI, in many cases they choose some random version of OpenMPI. And OpenMPI, well, Spectrum MPI is based on OpenMPI. The intercompatibility between 2 versions of OpenMPI is notoriously bad, so it might not those packages might not actually work unless they're recompiled against the libraries that are on the machine that we provide. Okay, native Python environment modules, they're also called Python. The environment module name is also named Python, but it will just have the major, minor, micro version for that Python interpreter. And from January 1, the defaults will be Python 3.7.0 and Python 2.7.15. Some of the older machines that were used for acceptance will also have some older versions of Python on them. I'd recommend use the latest. Python is relatively good at backwards compatibility within a major version. And I think right now on Summit, the default is Python 3.5.2, There's a lot of great features added to 3.6. If you haven't used them, 3.7 is even better. It came out earlier this year. Okay, so when you load a native Python environment module, you'll get some extensions that aren't in the standard library in that interpreter's site packages just by default. And there's some exceptions to that. The extensions that we put in the root site packages include virtualenv, pip, setup tools, nose, and they're really there so that you can load that Python interpreter and use it to create a virtualenv. There's a caveat to this, is that this is only true for the Python interpreter that gets loaded if you've got no compiler modules loaded. A quirk of the way that we deploy the software results in compiler environments. If you've got a compiler module loaded, they will actually get different Python interpreters. They'll all be the same version. The same versions will be available for each of them, but the actual binary will be different, which means the actual site packages for that interpreter will be different. So if you want to use the native Python environment modules to create a virtualenv, unload the compiler, load Python, use it to create a virtualenv, and then that's it. The virtualenv will have a link to the Python interpreter that was used to create it, and you don't have to worry about loading additional Python modules later. If you use that virtualenv, it's going to use the right interpreter. As I mentioned earlier, we're no longer providing lots of Python extensions via environment modules. You'll find some. You'll see some on the machines already. Sometimes we have to provide extensions by environment modules, for instance, MPI for Pi. And we're open to considering adding environment modules for some common packages, NumPy, SciPy, Matplotlib, as long as they're not optimized. But Python bindings for specific tools like PyNetCDF or HDF5, the combinatorics and maintaining those is impractical. And so we're not really interested in doing that. In general, if you want to install bindings for a language like that, we'd suggest you use a virtualenv or Conda. Oh, okay, I got ahead of myself. So this is the slide that covers everything I just said. One thing to be aware of is that we try to minimize this, but it is possible that loading a Python extension from an environment module doesn't actually load all the dependencies that it needs. Like I said, we try to minimize when that happens, but some things will slip through the cracks. Again, another reason why you really should use a virtualenv and have the Python environment completely under your own control. So if you do use a Python extension from an environment module, and it complains about not finding packages when you start your application and can't import something, this is probably why. And you'll need to load additional Python extension environment modules. And if that happens, let us know and we'll fix that environment module, the module file. Okay, providing your own extensions. Python really, it exists in user space in most cases. You can install Python packages and extensions anywhere and put them into your Python path. And so outside of really convoluted Python extensions like Matplotlib that require display servers and such, most Python packages are relatively straightforward and easy to install yourself. What you don't really want to do is pollute your Python path. And this is what happens with the extensions that we provide by environment modules. When we provide an extension by an environment module, the only way to make sure Python sees it is by inserting a path into your Python path. And the order that things get inserted into that path, or if Python packages built for, say, Python Major version 2 are in your Python path when you're trying to use Python Major version 3. This will lead to random runtime errors. And so putting lots of things into your Python path is not really a good approach to setting up a Python environment. And it is the fundamental reason why Python extensions being deployed through environment modules is a bad idea. The way to avoid that is to use a virtual env. You have a clean, empty Python path and all of your packages in one site packages directory. And there is no risk of cross pollution between Python versions or different machine architectures or external dependencies. One thing I'd recommend to people, I don't see this too often anymore, but we occasionally do see folks will modify their Python path in their shell init files. I advise against that unless you're really careful, and many of you are, because the home directory is shared on all of our machines. And so if you inserting things in your Python path that shell startup for use on, say, Summit, and then you hop over to Rhea, and those packages are still in your Python path, you'll have a bad time when you run into the architecture errors. Okay, so how to create a Conda environment. I think probably everyone here who uses Conda is already aware of this. Maybe I don't know how many people don't use Conda, but maybe will be using it. If there's any folks listening, this really is for you. It's very simple. You load the Anaconda environment module. That'll put a binary in your path Conda, and you can use it just like you would virtual env. Well, not just like, the syntax is different, but similar process. Conda create. You list a set of initial packages that you want to put in your Conda environment. You can specify what Anaconda refers to as a channel. It's a repository where it pulls the precompiled binaries for a given package from, and -p and specify a path to where you want that Conda environment to live. I recommend putting Conda environments and virtual environments on the NFS file system, ideally in CCS project ID. That's an area that's not purged. It has a higher quota than your home directory, and it's generally available everywhere. But you can also put them in, say, your home directory if you're going to use that environment from a resource where your home directory is available. So by default, this will create a Conda environment that's populated with packages that use precompiled binaries. In some cases, those binaries won't actually work the way you expect them to. Things like MPI for Pi, built against a different version of OpenMPI. In that case, you'll have to replace those packages in your Conda environment by building them from source. That's relatively easy to do. You can do that with pip. Pip is made available in your Conda environments. And this is the same thing that you would do if you're using virtual environments, using the native Python interpreters. But pip install -- no binary, and then you can give it a list of packages that you don't want to use precompiled wheels or binaries for, install, and then the package name. And this list can include dependencies for a package as well. You can actually also put, it's a keyword, :all : here as the argument to no binary, and it will build everything from source. Everything that pip has to pull in, provide this package, will be built with source or from source. To use the conda environment, you've got to activate it. The way this works, and if you're not using bash, my understanding that the conda activate script isn't really well written to work if you're not using bash or zeesh. But you have to source activate the name of your conda environment. Activate is a script that gets put in your path when you load the Anaconda environment module. And it has to be called using the source keyword, not dot. So source keyword is a bashism, as possibly one contributing factor to why this doesn't necessarily work well if you're using tees or sheesh. But this will strip all the other Pythons out of your environment, replace it with the Python interpreter and site packages that are in your named conda environment. And then when you want to stop using that version of that Python interpreter in that environment, call source deactivate. This is similar for virtual environments. Python 3 has virtual environments built into it. It's part of the standard library. And so to create a virtual environment, if you're using Python 3, Python 3-m venv, and then the path to where you want to create a virtual environment. For Python 2, the utilities to create a virtual environment are external tools that will get put in your path when you load a Python interpreter with no other compilers loaded, or a Python interpreter and you've also loaded the PyVirtualEnv environment module if it's available. You specify virtualenv path, and that will create a virtualenv that you get your own private copy of pip, set up tools, distutils, and you can install packages into that virtual environment as though you were root and there was only one Python on the machine. To use that that virtual environment, you've got to activate it by sourcing the path to your virtualenv bin activate script, and to deactivate it, you can call the deactivate shell script that gets put into your environment when you've activated a virtualenv. You can also activate your virtualenv by referencing the Python interpreter in your virtualenv. So if you've got a script and you want that script to always run under a virtual environment, a specific virtual environment, you can, in the shebang line of that script, place the full path to the Python version with the Python interpreter in your virtual environment. There's actually also another way to activate a virtual environment within a script, but really this is just easier, and anybody who needs to know the other way can find it themselves. I'd recommend that when using virtual environments, make sure you load all of the other environment modules that you will need before activating the virtual environment. And if you need to change a environment module, deactivate your virtual environment first. Lmod handles this better than Tcl environment modules did, but that's always going to be a safe practice, doing that, making sure that venvs are deactivated before changing environment modules. Yeah, it might work if you don't deactivate the virtual environment, but this is always a safe bet, and I've been burned enough by that to just always do it. Okay, so as far as building Python extensions from source, this can sometimes be tricky in an HPNC environment. Simple pure Python packages are relatively straightforward. You don't have to think about it, just pip install the package. But if the package requires a lot of external compiled dependencies, then it can be tricky. I kind of already mentioned this already, but cover it again, I suppose. Pip can install packages from source. You pip install and use the -- no binary flag. In some cases, whatever package that you're trying to build will need external dependencies. And one of the most common ways to configure the source build to use specific external dependencies is through the use of environment variables. If you set the CC and MPI-CC environment variables in the pip line to the compilers that you'd like to use, I recommend using the OS GCC whenever you can. Most Python packages are written in such a way that they assume you're using GCC. So setup.py and the make files that get called from setup.py for any given Python package, you'll find GCC-specific flags and assumptions in them all the time. So if you're using a different compiler environment, it might be helpful to ensure that you're forcing it to use GCC. Unless you don't want to. If you've got a specific reason to use a different compiler, go for it. You can also install packages completely manually from source by downloading the source code and running setup.py. And don't really have time to get into all the different ways that this can be done, but you may need to get creative to configure a package appropriately if going this route. And I would say look at the package's documentation. I found that a lot of times the package documentation is lacking because they assume you're using an Ubuntu laptop and it's like, oh, this is easy, just pip install it. And that's not always true in an HPC environment. If you have problems installing something, you can contact us. We'll be glad to help you walk through installation of a package. But in general, just using environment variables is sufficient. And I've got some examples in the backup slides here that go over other packages, like HDF5, for instance. When you install it this way, it'll look in the environment for a HDF5_dir directory. If you've loaded one of our HDF5 modules, it sets that environment variable. And so pip has everything it needs to install that package from source out of the box. Because the MPI compiler wrappers on Summit are the same as OpenMPI, you actually don't really need to do this on Summit, whereas this is essential on Titan. You have to set it to the create compiler wrappers. So Summit's a lot easier to use pip to build packages from source than some of our other machines. And there's just some general guidelines and thoughts. I'd recommend that people follow PEP 394, which is use the name of Python explicitly. You want to use Python version 2, call the binary as Python 2. You use Python 3, call it as Python 3. In all of the cases, everything that we provide and what Conda provides, they will alias Python, the binary name Python, to whatever version that module actually provides. And so it's ambiguous as to whether you're using Python 2 or 3. And if you write all of your scripts just saying user bin Python and your environment is not set up correctly, you might wind up calling the wrong interpreter. So if you're explicit, you won't have any problems. And of course, mixing Python environments is not a thing. You can't be using a Conda environment at the same time you're using a virtual env, at the same time you're using the system Python, all within one environment. You can have binaries that use one interpreter, running as a separate set of processes than something else that you're doing. But in general, because of this, it's not practical, really, to use the Python interpreters that we provide to run 2 and 3 at the same time. You can set up an environment where you can do that yourself, but it's 2018, and really, why is anybody using Python 2? Except for the certain OS vendors, but even they're starting to get on board and move to 3. I mean, I know I've ported Python 2 to 3 codes before. It's not that hard. It will save you a decade of headaches to just do it. Also, Python 2 is slated to be deprecated, I believe, in 2020. So they keep moving that clock back, though. You'll have time. Yeah. No. It was the Python. They knew what they were doing and they made that decision, and who knew it was going to last 12 years. Okay, and I'd avoid mixing virtual enums or conda enums and extensions that we provide from the environment for the same reasons that I had mentioned, that you really don't generally want to use Python extensions from environment modules, the way that they're loaded and insert things in the Python path. And then, be careful with pip install --user because home is shared on a variety of machines, and not all Python interpreters on all of our machines ensure that they are using a unique Python user base. Okay, so thank you for listening, and I'll be happy to answer any questions that you have. There's quite a bit more content in the backup slides here, so if I didn't touch something that you're specifically interested in, let me know, and I may have something about it. Question?
So what I'm curious about are, of course, with MPI for PI, it makes sense for us to not use pre-existing binaries. What I'm concerned about are what are the other Python packages that I have to do the same thing for, in particular packages that I don't know about that. Are you going to have like a list of packages like, hey, by the way, when you pip install, make sure you do the no binary option for these particular packages?
So in general, if a package requires external dependencies and you try to build it from source, if it's pulled in as a precompiled wheel, it may have those dependencies already satisfied. There'll be whatever version of the external dependency that was used to build that wheel. And I think most people who are using Python in large amounts don't actually care about what version of HDF5 they're using. If you do care what external dependency is being used for a package, you probably do already know if that package has uses external dependencies, things like bindings for HDF5, PyNet CDF. Some of the more trickier things are all the machine learning packages. And it's actually gotten to a point where if you go and look up how to install a machine learning package from their documentation, they'll just say install from Conda. Because the list of dependencies that it needs are so huge, they have to bundle that all together into a framework where they can deliver those external dependencies and the Python code all in one. And the people who are using those packages, like I said, probably don't care that all of these dependencies are not exactly the same as ones that we provide elsewhere in environment modules, but that's okay because it all runs self-contained. The exceptions you have to watch out for, I'd say, are CUDA, and MPI for Pi. And you don't really need to worry about CUDA, actually. You just need to worry if the precompiled wheel is using a CUDA version later than our firmware supports. That's almost never the case. So then that just leaves MPI for Pi.